So thank you everyone for coming and attending today's ICC Distinguished Speaker Seminar Series. It is my great pleasure to introduce Professor Doina Caragea from Kansas State today. Her research and teaching interests are in the areas of machine learning and data sciences, with applications to crisis informatics, security informatics, and bioinformatics. Her projects build upon close collaborations with domain knowledge experts like social scientists, security experts, and life scientists in this case, and aim to provide practical computational approaches to address real-world challenging problems. Professor Caragea received her PhD in computer science from Iowa State in 2004 and was honored with Iowa State University Research Excellence Award for her work. She has more than 150 published refereed conferences and journal articles. She has a strong track record of extramural funding with more than 12 million funding as PI, co-PI, or senior personnel from NSF and industry. I'm really excited that Professor Caragea is here. The podium is yours now.
Thank you so much, Duka, for the introduction, and thank you for inviting me to speak in your seminar. I'm sorry I can't be there at this time, but I'm still honored for the opportunity. I will go ahead and try to share my screen. And we'll talk about my project on social media to aid disaster response. Before I start, I want to acknowledge some of my current and former students who have contributed to this work. And I also want to mention that this project was funded by NSF through a big data grant. It's a collaboration with Penn State University and UIC, University of Illinois at Chicago. And the main goal of the project is to build tools to help disaster response teams identify useful situational awareness information that is posted by people affected by disasters on social media. We have mostly focused on natural disasters, although in the last year we have branched out to COVID-19 crisis. We have some preliminary work in that direction, although I'm not going to talk about that today. I also want to acknowledge AWS, who has provided credits for the computation in this project through a partnership with NSF. We all know that deadly disasters happen all the time. It seems like we always hear some news about fires, about hurricanes, about tornadoes, many other natural disasters. And not only that these disasters claim lives, but the cost associated with them is sometimes very high. As an example, year 2017 was declared to be the costliest year for natural disasters in the US. There were 16 natural disasters with costs higher than 1 billion. And in fact, some of these disasters had significantly higher costs. For example, Hurricane Harvey had a cost close to 200 billion. And when a disaster like Harvey hurricane happens, the traditional emergency lines can be overwhelmed, and somebody might need to wait on the line for a long time to be able to report some information or ask for help. In such situations, in recent years, people have turned to social media to post information about their situation. And there are lots of useful things that are posted on social media by individuals affected by disasters. At the same time, there is a lot of information that is posted by government organizations, by traditional media, by family and friends of affected individuals, and sometimes people that are not even aware of the disaster will post about very different things. So one question is how to get that information that is useful to response teams in terms of gaining situational awareness. And that's a very difficult task when it comes to social media. Responders are faced with information overload, and due to this, they usually don't even look at social media. So the tools that we are trying to build is to help them with the information overload. Of course, one way to find this information is to simply do some Twitter search, and we can search Twitter using keywords. We can search Twitter based on location, but both keyword-based searches, location-based searches are very noisy and will retrieve lots of non-relevant tweets. And of course, manual selection is not an option, as it is very time-consuming, expensive. Therefore, we need tools that can automatically filter relevant, informative, and actionable information that is posted during disasters. Towards this, machine learning, in particular supervised learning, is one potential solution. But for an emerging disaster, we have no label data, and supervised machine learning will require label data to train classifiers that can be further used to predict more data. So a better alternative, which is the one that we have used in our work, is to use domain adaptation solutions where we rely both on label data from some prior source disaster, for which presumably some label data is available at the current time, and then unlabeled data from the current target disaster, and we build classifiers that are used for that target disaster. So with that in mind, we have designed a system for a system based on domain adaptation algorithms that are facilitated by AWS services. And the idea is that as soon as a crisis emerges, as a disaster emerges, and people start posting information on social media, we start crawling tweets. We mainly work with Twitter. And those tweets will be stored in a local repository, and at the same time will be sent to the domain adaptation module that is communicating with our repository of data and models, and is trying to identify source disasters that are similar and relevant to the current target disaster. And using models trained on those prior disasters, we can start making predictions right away. The predictions that are made with high confidence are sent to a human analyst that is validating those predictions, and they are synthesizing the actionable information in a form that can be sent to 911 dispatchers and subsequently to the responders. And tweets that are validated by human analysts are sent back to the domain adaptation module, which keeps evolving and improving as more data becomes available. So this is the high-level vision of our project. We rely on Twitter data, as I said. We generally use Twitter streaming API to crawl tweets that are posted during crisis events. We collect JSON files and parse them to extract information like tweet text, images, hashtags, some other information about user geolocation when that's available. And then we use domain adaptation approaches to classify tweet text and or images according to different categories. And in particular, we take a hierarchical approach to classifying useful information. We generally start by looking at tweets that are relevant to disaster, so that we filter out those that have nothing to do with a disaster. Then among those, we want to identify the informative ones. And for the informative ones, finally, we want categories like damage, injured people, donations, other things like those. In our early work, we have used traditional machine learning to design domain adaptation approaches, and we have looked at parameter-based adaptation using simple classifiers like naive Bayes with self-training. We co-learn from the source and target data. We have used feature-based adaptation. In this case, we've tried to make the source and target features more similar, and then presumably the classifiers learned on source are better after this transformation. And we have also used hybrid feature instance adaptation, again, using the simple naive Bayes classifier with matrix factorization as feature adaptation and KNN for instance adaptation. In our more recent work, we have focused on domain adaptation, in particular feature-based adaptation using deep learning. And the idea here is that generally the source and target domains will have somewhat different distributions. Disasters happen in different locations at different times, affect different populations. So they are generally different in terms of their distribution, but they share some patterns. And the goal is to perform feature adaptation, in other words, to transform the source and target data representations so that the source and target distributions become indistinguishable. And if they become indistinguishable, then we can use the classifier learned on source data to predict target data. We have used different deep learning implementations of this idea to build models for classifying both tweet text and tweet images. And I'm going to briefly describe one of the approaches we've used on images. In particular, we use the domain adversarial neural network approach to identify damage images. The approach was similar to an approach proposed by Gan et al. In 2016. It has as backbone a convolutional neural network, given that we are working with images. And in particular, we use the VGG19 architecture that was pre-trained on ImageNet, a large collection of images. This is the main architecture of VGG19. And overall here, we have our model architecture. With this CNN backbone, we look at two main tasks, a prediction task, and the prediction task is trained using source data, and we want to distinguish between damage and no damage. Again, we know that source data is labeled, so we can train the model to distinguish between damage and no damage. And then here, because our target data is not labeled, but we want to make source and target representations look similar, that we have a discrimination task where we are trying to discriminate between source and target examples. And this backbone of the two tasks can be seen as a transformer, where we are transforming the features to make them indistinguishable, source and target features. And the idea is that with this domain adversarial learning, the features, source target features become indistinguishable, so that even a good discriminator can't discriminate between source and target. We have used this model to predict disaster, to predict damage, no damage, in a set of disaster images published by Nguyen et al. In 2017. In the original data set, there were 3 damage classes: severe, mild, and none, no damage. But there was a lot of overlap and noisiness between the severe and mild classes. So we decided to combine those into a damage class, and then we trained models to discriminate between damage and no damage. There were 4 disasters in this data set: Nepal earthquake, Ecuador earthquake, Ruby typhoon, and Matthew hurricane. The nature of these disasters gives us the opportunity to study domain adaptation between similar source target disasters and more different source target disasters to see how the models behave. And I also want to mention for Nepal earthquake, we had lots of images. Ecuador, an okay number. Ruby typhoon, the data set was smaller, and for Matthew hurricane was very small. So as experimental setup, we performed experiments with all possible source target pairs of events. So we had Nepal earthquake as source and all the others as target. We consider one at a time as target and all the others as source, as we'll see in the experimental results. We trained the domain adversarial neural network models using all the source data that was labeled, and 20% of the target labeled that was used as unlabeled, just to do the feature transformation and learn the discriminator between source and target. We tested the models on 20% of the data, and we compared the results with results of supervised CNN network, supervised VGG19, that was trained just on the source data. As performance metrics, we used standard metrics like precision, recall, F1 measure, and accuracy, but we generally emphasized recall with the assumption that responders would not want to miss important information, useful information, and as presumably there is a human analyst in the loop, they could filter false positives if needed. So these are the results where Nepal earthquake was used as target. And here we are showing precision, recall, F1 measure, and accuracy. The blue bars represent the VGG supervised, learned just from the source data. The orange bars are the results of the domain adversarial neural network models. And we see here that for precision, if we are using Ecuador earthquake as source for the Nepal target, precision is better with a model learned on source itself. And it somewhat makes sense because the 2 disasters are very similar. Surprisingly, even for Ruby typhoon and Matthew hurricane, the supervised models are doing pretty well when predicting Nepal. And I want to remind you that Nepal was the disaster with lots and lots of data. So Matthew hurricane had the smallest amount of data. When we look at recall, though, the results using the domain adversarial neural networks are very similar to those using the supervised CNN, when Ecuador earthquake is used as source. For Ruby Typhoon and in particular Ruby Typhoon, the domain adversarial neural network is giving better results than the supervised. And we see the same pattern for F1 measure overall. If we look at Ecuador earthquake as target, again, in terms of recall, all the models, the domain adversarial neural network models are better than the supervised VGG network. And it's about the same for F1. Similar results when we are using Ruby Typhoon as target. In some cases here, when I use Nepal earthquake as source, the results increase from about 50% to about 80%. That's a significant improvement. And same for Ecuador, we see a good improvement for Matthew as source. The VGG is still better here. And finally, when you use Matthew hurricane as target, see similar patterns. Nepal earthquake, the domain adversarial neural network model is better. Ecuador earthquake, the domain adversarial neural network is also better in terms of recall. And for Ruby Typhoon, the two models are comparable. So here we are looking at the hurricane versus the typhoon. Given that they are somewhat similar, the results are similar. If we look at some images that are classified correctly as damaged by the domain adversarial neural network and misclassified as no damage by the supervised VGG, we see that all these images have some water. So the domain adversarial neural networks are able of understanding that this water in the images will suggest damage. However, they overuse that feature. Here we are looking at some images that are misclassified as damage by domain adversarial neural networks and correctly classified as no damage by VGG supervised learning. So again, there is some water feature in all these images, and somehow the domain adversarial neural networks learn to associate damage to water. But not always. Here are some images that are misclassified by both domain adversarial and VGG. So sometimes the models agree in terms of the mistakes that they're making. So as conclusions for this part of my talk, the results of the domain adversarial neural networks are similar to those of the VGG supervised learning for pairs of similar disasters. The results of the domain adversarial neural networks are generally better than the results of the baseline VGG supervised learning for different disasters, in particular for recall. So we also looked at domain adaptation. We also designed domain adaptation approaches for text classification. And in particular, in this work, we used the domain adaptation with reconstruction classification networks. So this approach was similar to an approach proposed by Ghifari et al. In 2016 for image classification. Here, the backbone of the model is a sequence-to-sequence network, in particular a network that consists of two long short-term memory networks. And those two networks perform the target reconstruction. The first LSTM can be seen as an encoder of the target text, target tweets, while the second LSTM is seen as a decoder. So we are doing some transformation of the target data while we're also learning to predict relevant and non-relevant tweets using the source label data. So in the process, just like before, this common component of the two tasks will help with the representation of the source target features so that they become somewhat indistinguishable. And in the end, we can use the model that is learned on the source to predict the labels for the target. To evaluate this model here, we used a disaster tweet dataset that was published by Alam et al. The tweets were labeled with respect to two classes, in particular, relevant and not relevant. There are two crisis events in this dataset, again, Nepal earthquake and Queensland flood. And the authors of this paper provided also train validation and test subsets for each of the events. And we used the same so that we can compare with the results. In their work, they used a domain adversarial model in combination with graph embeddings. So we performed experiments with both Nepal earthquake as source and Queensland flood as target, and the other way around. The trained models were the models were trained using all source data, which is labeled, and all target train data, which was used as unlabeled. And of course, we tested the models on the target test data because ultimately we want to see how they perform on target data. We compared the results with the results of supervised LSTM and CNN because it was used by Alam et al. As a baseline. And then we also compared with the results of the approach from Alam et al. That, as I said earlier, was based on graph embeddings and domain adversarial training. As performance metrics, we used the area under the ROC curve and F measure. So here are the results that we obtained when we used Queensland flood as target. The yellow is the LSTM with reconstruction, the domain adaptation approach. The gray is the supervised LSTM. Orange is the graph domain adaptation that was used by Alam et al. And blue was the CNN. So we see that our domain adaptation approach outperforms all the other approaches, both in terms of AUC and F1 for this pair of source target disasters. The graph domain adaptation is better than both the CNN supervised learning and the LSTM supervised learning for this pair. If we look at Nepal earthquake as target and Queensland as source, the domain adaptation approach is still the best. The LSTM supervised model is the next best in this case, better than the graph domain adaptation that was proposed by Alam et al. And they are all better than the CNN models. So as conclusions here, the results of the LSTM with reconstruction are better than the results of the supervised baselines, CNN and LSTM. And they're also better than the results of the graph domain adversarial model proposed in prior work for both pairs of source and target events and both metrics that we considered. The results of the graph domain adaptation are better than the results of the baseline CNN, but they are not always better than the results of the LSTM. So with this works independently on tweet text and tweet images, We next ask the question, can we improve the results of tweet classification in general, in particular, multimodal tweets, in the sense that we have both text and images in those tweets? Can we improve the results if we consider both modalities together? And in some preliminary work, we try to combine the text and image, and we noticed that we can't always improve the results as compared to text and images. And a closer look at text and images coming from the same tweet revealed that there are different types of relationships between the image and the text in a tweet. In particular, sometimes the tweet and the image are completely unrelated. A small percentage of tweets that have both modalities, both text and images, will show this unrelated relationship. A good number of tweets will have a similar nature, so we have a similar relationship between them. And then for some tweets, we have somewhat a complementary relationship. In fact, we annotated a set of about 5,000 tweets that have both image and text. We use Amazon Mechanical Turk to annotate those tweets. And out of those 5,000, about 4% of those tweets showed the unrelated relationship. Almost 60% had a similar relationship, and about 30% had complementary relationship, and then all the others were that the annotators did not agree. So we mostly focused on similar and complementary relationships, given that those were more significant in the data set that we annotated. And with this type of relationships, similar or complementary relationship in mind, we set to train models, multimodal models for two tasks. In the first place, we wanted to train models that can identify this image-text relationship in multimodal disaster tweets. So we want to be able to train models, multimodal models that can classify the tweets as having similar text image or complementary text image. And then we want to see if we can use this image-text relationship as an auxiliary task, an auxiliary piece of information to improve multimodal disaster tweet classification. And for the first task, the task of identifying text-image relationships, we used several approaches. In particular, we used what we called concat bag of words. Here we concatenated ResNet features. This is another pre-trained CNN network. And also average glove word embeddings for the text. So we concatenated those two representations for images and for text. And then we used the linear layer for classification. As another approach, we concatenated word embeddings. These are contextual embeddings with ResNet features representing images. And then, as before, we used the classification layer on top. The next two models here, multimodal byte transformer and vision and language BERT or VIL-BERT, these are models where the text and images are co-trained together, the two modalities, so that you end up with a representation that reflects both the text and image. And we used these approaches on the data set that we annotated. We have the 4 approaches, and we are reporting precision, recall, F1. And as we see, the 2 inherently multimodal approaches, the MMBT and Wilbert, are better than the other two approaches where we are concatenating features for text and features for images. And in particular, Wilbert is a little bit better than this MMBT model. And then in the subsequent task, we wanted to use the relationship information, the model that we're training on our helper task, on our relationship identification task, as so we use that in addition to the actual model for classification. We got an embedding from this helper task. We got an embedding from the main classification task. We concatenated those embeddings, and then we had a classification layer and use that to make predictions. And here we use the multimodal dataset that is called Trace MMT dataset, published in Alam et al. In 2018. Another paper by Alam et al., not the one that I mentioned earlier. And they had some humanitarian categories and then damage assessment categories like the ones that we saw earlier. And here we are looking at MMBT versus MMBT that is augmented with a relationship between image and text, and then Wilbert and Wilbert augmented with a relationship. And we are reporting precision, recall F1, micro values, and macro values. And we see some improvement in general, not always. For example, here, the MMBT with this augmented information does not do better. But in general, we see a little bit of improvement between the models that are the multimodals that are just using the text and the image versus the models that are using the relationship information. So we concluded that the multimodal models can be used to predict the relationship between the image and the text of a multimodal disaster tweet. The image and text relationship can subsequently act as a proxy to boost the performance of various multimodal disaster tweet classification tasks. And in our ongoing work, we are looking at using multimodal data, text and images, with a noisy student model to improve the predictions on a target disaster. So here we have presumably labeled data from a source like before, and we are training a teacher, Wilbert, VisualBert, a multimodal type model. And then we use that to predict pseudo labels on unlabeled target data. And we inject some noise into the student model and train VisualBert student model with combined data and noise injected, and make the student a teacher and repeat this process to end up with models adapted from the source to the target. So that's our work on domain adaptation for images, for text, and then our ongoing work towards using both images and text together with multimodal models. In related work in this bigger project, we looked at localizing and quantifying damage in social media images. And here we used a CAM-based approach, again with VGG19 as a backbone network. The idea was to train a VGG19 network to predict between damage and no damage. And then we are taking the gradients with respect to the damage class that we are interested in, and we're propagating them back and using the features of the last layer here with some weights coming from these gradients to construct a damage detection map that shows a heat map of where the damage is in a picture. And then by using the pixel values in this type of image, we can also come up with a damage assessment value. So we evaluated this approach on a data set that we crawled from Google. In particular, we had 308 damage images that we crawled using keywords Nepal building and damage. And we had 311 no damage images crawled with keywords like Nepal and city. And we split our training data, our data into training and test, and we performed some qualitative analysis, mainly analyzing the heat maps of damage, no damage, to see if visually they look accurate. And then we performed some quantitative analysis in terms of using the intersection over union metric to evaluate damage localization. And as part of our qualitative analysis, we had some images that show damage. Those on top show damage, and those are their corresponding damage maps. There is a lot of red in those images, and that's the kind of what the model finds to be the worst in terms of damage. We can also calculate the damage assessment value based on the pixels of the values of the pixels in those images in the heat maps. And then here are some images that don't show damage, and their corresponding heat maps that barely show any red. And of course, the damage assessment values are very small compared to the damage assessment values that we got for the damage images. And when we did our qualitative analysis in terms of intersection over union, we for 10 images, we had 2 human annotators annotate those images. It's obviously a very subjective task. Like if I look at this image, what do I consider damage there? And this is what one annotator marked, and this is what another annotator marked. And this is based on our model when we use that threshold, I think, of 20%. So we did, we looked at agreement between, in terms of IOU, between annotator A and our damage map, annotator B versus our damage map, and A versus B. Overall, the 2 annotators had an average of 0.610 as agreement. Our damage map had an agreement of 517 with the second with annotator B, and 380 with annotator A. Overall, the 517, 0.517 looks pretty good. And if we look at some specific images, there are cases where our models agreed more with one of the annotators than the annotators agreed among themselves. So our study has shown that it's possible to use social network images for post-disaster damage assessment. This can prove to be an inexpensive alternative to more expensive GIS approaches. In a follow-up study, we looked at other types of damage, infrastructure damage. We looked at bridges, we looked at buildings and road damage. And in future work, we are asking the question, can we aggregate the damage as maps of images posted during a disaster to construct a global damage map like shown here. Of course, for this, we would need to have location information, and most of the tweets don't have location information. So the next question that we are asking is, can we use the actual tweet text to identify geolocation? Many people, when they post something actionable information, they will also post some location information. And of course, another important work that needs to be done here is in terms of reliability. Sometimes people post false information in relation to a disaster, so we need to be able to identify what is real information and what is fake information. And that's also a big challenge, especially when an image like this is actually real. So lots of challenges and lots of other problems that can be, that will need attention to make this type of work usable by response organizations. But we are still moving into that direction. We are still working on that. I think that's all I have. Thank you very much for your attention, and I'll take questions.
Yay. Hi, Doina, this is Tim. So we're sitting here with Duka and another student as well. So we have a mic open, so we'll open and close it when we have questions. But I'll start off with the question, and then we'll open it up. So from working in this area, I know that one of the big challenges is finding large enough data sets for the size of the networks that you can get performance like this in, where there's millions of parameters to a network. So could you comment on what you've done to ensure that the results that you're getting aren't affected, say, just by data set bias and the small data sets that you have?
Yeah, that's a great point. And labeling data, especially large data sets, that's definitely a challenge. Fortunately, there is a group that we are collaborating with in Qatar, who has done a lot of data labeling in this domain. And more recently, there is also a group in Europe. They have established somewhat of a challenge for this domain, and they have also gathered various publicly available data sets into a larger repository. And having some standard data sets, people could compare between different approaches and could ensure that progress is made. And one approach is better than another when you're using the same data set. But again, I definitely agree that labeling large data sets is challenging. We have labeled a few ourselves. Some were better than others in terms of the quality that we got, and it gets expensive.
Thank you. Nathir, you have your hand raised.
Yes, my virtual hand. Let me put it down. Thank you, Professor Doina. Very interesting. I have a question about the image pre-processing. I mean, the images are probably of various resolution, contrast, and what did you do to make them uniform as a uniform input?
We generally resize them to whatever the input of the network that we are using.
Do you do a grayscale conversion, or do you use the color information?
We usually use the color information. We don't do a grayscale conversion, but in some cases we use some data augmentation. So we do some transformations of the images.
I have one last question. I did not understand the pixel-wise damage localization that you showed. Can you explain that again? Thank you very much.
Sure.
I mean, I wonder how you were able to produce that heat map. Was it automatic?
It is automatic, yeah. This gradient weighted class activation mapping approach is essentially localizing in the image the important part, what the network found to be useful in terms of predicting damage. So we are taking the gradients and we are weighting these features at the last layer here and ending
Very
up
good.
with a repainted image.
Thank you. That's great. Thanks a lot.
So it's one of the explainability type approaches that can also be used to do localization. We are looking at what in the image the model found useful for making the prediction that it made.
So Doina, this is Tim again. I actually had a follow-on question regarding this. Since you were using an explainability method for, and then actually like flipping it on its end and saying, hey, we're going to use this to detect damage. Did you do any fine tuning after this to improve upon that? Because I know from looking at especially these types of explainability methods with deep networks that sometimes you can find that inferences are made from things that you didn't actually expect that they would be made from, some stuff in the background, which is why these are really good for use. But did you find that for the most part that this ended up to be a really good damage assessor, even though you're not actually training it to be such a damage assessor in this case?
Yeah, it turned out to work pretty well. It generally highlighted the regions where you would see most damage, but like if you look here, there was a building and maybe that's the worst damage. But the whole image shows a lot of damage, the network just. What we found harder was to find a good threshold for when we binarize the damage. If we want to find this binary mask, what's a good threshold, how on the pixel values, so that we can match better. And that somewhat varies from image to image, if you wanted to match what the annotator said. So we did some fine tuning and we came up with an overall good threshold. But
so you're showing here like the images that look good when they're doing the damage assessment with this explainability method. What happened, for the images where this didn't work out so well? What did you find? Did you find any patterns of behavior that could allow you to improve results into the future?
We did not find any patterns, and I don't know for sure now how would some images where the results were worse would look like. I don't have any examples here, but again, overall, and this was a study with a small data set just because it's more of a visual study. And in general, when there was damage, the models found quite a bit of red regions here. When there was no damage, there wasn't much shown.
Okay.
But yeah, we could look further and try to find some other patterns for those images that may not be.
Yeah, I always think it's fun to see not only the images where things work out well, but the images where things don't work out well. And I'm curious what those look like.
I agree. I don't remember right now what happened in that case.
So Doina, this is Duka. Just a follow-up question on what Tim was asking earlier. So in terms of that, the other work where somehow like your model learned that if it was water, it was kind of damaged, right?
Yeah.
So what could be the possible reason? Is it that most of the images that were damaged, labeled as damaged, had water?
Yeah, there were a lot of hurricane type images in this data set. Well, there were also earthquake images, but well, yeah, the Ruby typhoon. That's just a feature that this adaptation model picked, and I don't remember right now from what was the source, what was the target here in this model.
Mm-hmm.
But it could be that the source is a hurricane and the target could be an earthquake. I should have put that information on the slide, don't remember. But yeah, it probably has some bias from the source disaster.
Yes.
It might have seen images with water and associated damage to water.
Right.
Thank you.
Actually, I just have a quick question. I was wondering, was alternative text in the Twitter images used at all in the modalities when you're looking at text of images and the images themselves for visually impaired? Was the alternative text used at all in the classification?
No.
Okay.
In principle, that could be included, but we did not.
What about if you, any feature extraction, wavelets or anything like that, pre-processing before you put them in? Have you tried things along those lines?
No.
All right, I mean, we did a lot of that in the past, but I assume that the deep learning models are probably sophisticated enough that they sort of get past the noise and find the features pretty quick themselves.
Yeah, the CNNs that we have used are the feature extractors.
Yeah.
In all these models that we have used. Yeah, they make it pretty easy to work with images these days.
So Doina, I noticed that you moved from LSTM architectures to transformer architectures as you progressed in your research.
Yes.
Did you go back and try the transformer architectures on the tweets data to see if you got any additional performance gain with those?
Not that model in particular. Would be interesting to do that. The student who has done that work has graduated and don't have another student right now to do that. But I expect the results would probably improve even more because all the subsequent works we've done where we compare LSTM with BERT with transformers, the transformers were better.
Mm-hmm.
It's hard to beat them even with more sophisticated approaches. Results with BERT are generally pretty good.
Yeah, transformers are ruling the roost right now.
Yes. We're using some capsule networks in a different related project. And there are other works that claim that those networks have done better than lots of baselines, but they have not compared with BERT. And we compare with BERT, they can't beat BERT. So we'll have to report some negative results in a way for the capsule network. But we will present our comparison and show that while other works have found those capsule networks to give good results compared to a variety of baselines, in our case, they don't give better results than BERT.
All right, if that's the case, thank you so much, Doina, for presenting your work. This was a great presentation and it's really exciting results to see. And I think you probably inspired many people to think about collaborating. So thank you.
Thank you so much. And I would be happy to talk to some of you about possible collaborations. I have already some collaborations with Duka, but I would be happy to talk to other people. Thank you.
We'll give you the Zoom clap again.
Thank you.
Thank you.
Bye.
Bye.